Welcome to everyone to this lectures on combinatorics, week 3. In the previous previous 2 weeks, we looked at pigeonhole principle in the first week and several of its applications. And then we went to look at several basic counting techniques in combinatorics that one can use, like the addition rule and product rule, and some other interesting results related to this. And then we looked at some applications. Now we are going to look at further applications of these basic techniques to develop a little more advanced tools or results that we can use in many situations. And that is what we are going to do in this week's lectures. So we start with a very interesting problem. Okay, so it is the following. So consider the equation summation xi is equal to n, where I ranging from 1 to k. So x1 plus x2 plus etc. xk is equal to n. Now xi's are restricted to be non-negative integers, that they can take value 0, 1, 2, etc. Now given this condition, look at any possible solution to this, right? So any solution to this equation can be described as a k-tuple, something like a1, a2, etc., ak, where ai is the value taken by xi, where xi can be, let's say, 0 or 1, 2, etc., right? So if x1 is equal to 5 and x2 is equal to 7, then we will have this tuple starting with 5, 7, etc., where a1 is equal to 5, a2 is equal to 7, right? Such a tuple is called a weak composition of n into k parts. K parts because, we are basically writing n as a sum of k non-negative integers. Okay, so this is called a weak composition. Now, before trying to find out, our ultimate aim is to try to count the number of possible weak compositions here. But before that, let us also look at a slightly different definition, where we allow xi to be strictly greater than only to be strictly greater than 0, that xi cannot be 0. Okay, so if you have equation exactly the same, right, x1 plus x2 plus etc. xk is equal to n, where xi is strictly greater than 0 to be a positive integer, right? Xi's are positive integers. Then again, any solution given by the ordered tuple a1, a2, etc. ak, where ai belonging to n plus is called a composition of n into k parts. So it's not weak composition, it is composition. So maybe at later point of time it will be clear why it's called weak and the other one is to be not weak, right? But for the time being, let us just take the definitions for granted. Now, can you think of any argument to count this number of possible compositions or number of possible weak compositions? Okay, so I tell you that both of these can be solved by some results that we already looked at. Okay, so with this information, can you think about this and find a solution by your own? So maybe you should spend some time, pause this video, spend some time trying to figure out how to count these two things. Okay, it will be very useful if you spend some time thinking about this instead of looking at the solution that is presented here. Okay, so here it goes. So we will first try to solve the second question, that is to count the number of compositions of n into k parts. Okay, so since we want to make our the lectures, or we want to remember the lectures to be sweet, let us convert this question into a more enjoyable form, right? As follows. Okay, suppose we are given let us say n, which is greater than or equal to k. Let's say ladoos. Okay, so n ladoos, like identical, same kind of ladoos maybe, or Tirupati ladoos maybe, one of the most famous ladoos, tastiest. And they are given, and we want to distribute it to let's say k children. Okay, so if you think that you are children, then maybe you can hope to get some ladoos, right? Now, so we have enough ladoos so that we don't have to be like we don't have to be very selective, right? So we can say that every child is going to get at least one laddu. That I will guarantee. Okay, so everybody will get at least one laddu. Then how many ways you can give the laddus to the K children? That is the question, right? Because even though I said that everybody get at least one, I did not say everybody will get equal number of laddus, right? But at least if you get one, you can be happy. So we will make sure that everybody gets at least one. So now the question is that how many ways we can distribute the laddus? Now one can immediately see that this question is precisely the question of composition, right? Because now you can assume the number of laddus received by each of the k children to be the values taken by xi's, and they sum to n, and then the number of ways to do the distribution is precisely the number of solutions to this previous question of composition of n into k parts, right? Because xi's are to be strictly positive, everybody gets at least one, and it should be integers, so everybody gets at least one. Now, how do you solve this question? Again, think of laddus if it helps, and try to figure out how to do this yourself. If that doesn't help, we go to the next page. Okay, so let us assume that there is a hall where the children are waiting, and then there is a table where all these laddus are kept in a line. Okay, so we have these laddus which are kept in a line, right? So laddu 1, 2. I think I took the wrong tool. Laddus, yeah, 1, 2, 3, etc. Right? All the n possible laddus are there. Okay. Now, this is supposed to be n. So all possible laddus are there. Now they are kept in a straight line. Okay. Now we want to distribute the laddus to the children, right? So how do you do? Okay, we will say that okay, children queue up, right? So okay, stand in a line. So the child number 1, number 2, etc. stands in one line, right? So they stand in a line, and then we will say that okay, see the first child can start at the beginning, right? The first person starts at the beginning here, or maybe I will even use this. So start here, right? Because now we want to use all the laddus, right? So we will say that okay, you start at this, at the very beginning, the first guy in the queue. Then you start taking some laddus, right? And once you take some laddus, I don't know, 1 or 2 or something, right? Some number, whatever, maybe 5, depending on the person who is standing there. Okay, now go, right? So once he has taken some number of laddus, we will say okay, now the next guy in the queue comes. Okay, so the C2 will start at this place, right? So the child number 2 starts at the position which is after the first guy is asked to leave. Again, he will take some laddus, and then suddenly the person who controls the queue says that okay, you leave, next guy. So this way, each child will be allowed to go and take something. Now, since everybody gets, we need to make sure that the last child gets at least one. So he should start before the end, and then he should be allowed to take whatever is remaining, right? Whatever remains should be given to the last child, so that all the n laddus are distributed to the k children. So this way we want to make sure that everybody gets at least one laddu. Now, how many ways this can be done? This is easy, because what we have is that we have to decide where each of the children starts, right? Now the first person doesn't have a choice, right? So we don't have to look at that, because he always starts at the beginning, right? So therefore we need to only decide the remaining k minus 1 children, right? 2 to 3k, where they are going to start. Now they can only start at some point in between, like in these laddus, right? So there is n laddus which are kept here. Let's say 1, 2, 3, etc. N laddus are kept here, and therefore now the positions where the children can start are in between these laddus, right? So if there are n laddus in a line, how many gaps are there in between? So there are exactly n minus 1 gaps in between. So out of these n minus 1 gaps, we need to decide which are the positions where the k minus 1 children are going to start taking the laddus. So once we know that, we know the number of ways you can do that situation. And how many are there? Well, since there are n minus 1 gaps available, and we need to select k minus 1 of these gaps where the children can start, n minus 1 choose k minus 1 possible choices are there, right? So these are the number of available choices, and each choice correspond to a composition, and every composition corresponds to one of these choices, and therefore this is a one-to-one correspondence, and we get that the number of possible compositions of n into k parts is n minus 1 choose k minus 1, or is equal to n minus 1 choose k minus 1, right? Yeah. So this is the number of compositions of n into k parts. Okay. So is that clear? Now, what we are going to do is now to look at the first question, right? What was the first question? We wanted to look at the weak composition, right? Weak compositions are the solutions xi greater than or equal to 0 instead of xi strictly greater than 0. So we found out that the number of compositions is precisely the ways of distributing sweets to children, right? So we had a great time solving this. Now we want to solve the other question, right? So here is a theorem which says that the number of non-negative integer solutions to the equation x1 plus x2 plus etc plus xk is equal to n is given by n plus k minus 1 choose n. Okay. Now, how do we prove this, right? Now, since we already solved a question of composition using sweets, why don't we try the same thing, right? Maybe we can still work with sweets. So let us start by assuming that let x1 to xk be the number of laddus children got when n laddus were distributed to them, right? See, n laddus. So here also we are doing the same thing, right? We have n laddus. We are going to distribute them to children, but now the person standing at the queue may not be fair, right? He will say that, okay, some children who comes, I don't like you, right? So you don't get anything, right? This is possible, right? So there is somebody standing there. You will say, okay, first guy come, okay, you take something. Second guy take something. Third guy, no, you go, you don't get anything, right? Then fourth guy. So this way, we can make some of the x's to be 0, right? So when the distributor is unfair, then this can happen. Now, can you convert this to the previously solved problems? Any one of the previously solved problems or the previously solved problem just before, right? If you can convert it to a previously solved question, then that is the best thing to do in mathematics, right? Because you reduce the problem to an already solved problem. So if you can do that, then we are done, right? If you can convert into a previously solved problem, then that is it. So how do you convert it to a previously solved question? So again, I want you to think about how to convert this to the previous question, right? So can you convert the unfair distribution to a fair distribution question? If you can do that, then that is good. So this is quite easy actually, right? Because we want to distribute n sweets to k children, so that everybody gets. Some kids may not get anything, but now we want to convert into the question that everybody gets at least one. Now, how do you make sure that everybody gets at least one when some of them can clearly be 0, right? So what you do is that you assume that from each children before the distribution, right? For each children, we will go to the child and say that, okay, we are going to distribute some sweets, but now since we don't have enough, can you please give us one laddu each, right? So from every child you borrow one laddu, right? So you take one laddu from each of the children. Now keep it with you. So now you have k extra laddus, right? So you take the k extra laddus and then put that also in the table. Now you again send the children back to the queue, right? Now whenever a child comes, he will definitely get at least one, because he gave one laddu to the distributor. Now no, this guy cannot say that, okay, you don't get anything, because he will say that, okay, I already gave you one laddu, I should get at least that one back. Now what does this mean? This means that everybody gets at least one, which means that you get xi strictly greater than 0. But now for every solution to the weak composition, or the solution to the distribution where xi can be greater than or equal to 0, we have a solution where xi is greater than or equal to 1, or xi strictly greater than 0, right? Because you just add 1 to each of the xi's, and on the right hand side you have, instead of n, you have n plus k, because we started with k additional laddus, right? So therefore, distributing n laddus to k children, where everybody gets greater than or equal to 0 laddus, is equivalent to saying that distributing n plus k sweets to the same k children, where everybody gets at least 1. Because whenever you have a solution to at least 1, you remove 1 from each of them. You have k less laddus, right? N plus k minus k, which is n laddus. And some of them can become 0 now, because xi was 1, it will become 0, right? So there is a one-to-one correspondence between the solutions, so they should be the same. So that is it. So we have already converted it, right? So we said that, okay, solutions to xi plus etc. xk is equal to n, xi greater than or equal to 0, are in one-to-one correspondence, right, with the solutions x1 plus etc. xk is equal to n plus k, where xi is greater than or equal to 1, or xi strictly greater than 0, right? Xi greater than or equal to 1. And we know how to do this because we just did in the previous exam, right? It's basically whatever was that number n plus k minus 1, choose k minus 1, right? Which is equal to n plus k minus 1, choose n also, right? By the property of binomial coefficients, right? So therefore, this is what we wanted to prove. N plus k minus 1, choose n. So we already have the solution, right? N plus k minus 1, choose n. So this is one way we can prove this. Now let me give you another proof, okay, to the second, the first question, weak composition. So the proof 2 is also quite nice. This is by using another result, right? So what we do is that we observe that the number of ways to distribute the laddus to the kids can be made as follows. Okay, so you keep your n laddus here. Okay, so the laddus are here, this one, this one, this one, etc. All the n laddus are kept here. Now once these laddus are kept, what we are going to do is that we separate the laddus by putting some markers or sticks in between them. Okay, so here are the sticks, right, which separates the laddus. When of course these the sticks can be together so that there is no laddu in between. That is also possible, right? So we keep some bars or k minus 1 sticks in between to separate the laddus. Now the sticks, once they are kept, this decides the composition or the distribution of the laddus, because you will say that okay, the first child can take all the laddus till the first stick. If the first stick is in the beginning, then that guy does not get anything, right? So xi can be 0, x1 can be 0, right? Similarly, after the first stick, so the laddu is taken, the first stick is removed, and then say that again second child now go take the laddus till the first stick again. I mean the second stick, which is the remaining set the first or the next stick, yeah, right, till the next stick. So from this to this, again the third child goes and take the laddus till the third stick. Right? So this way the k minus 1 children take, and the remaining laddus, if there are any, because if the stick is at the last end, then there is nothing remaining. So which means that the last guy also may not get anything, right? So you can take, right? So this is basically you have the laddus and sticks, and then you are arranged. You put the so as I told you, some of the sticks can be like this, right? You can have 2 sticks like this, so that after the first guy, the second guy does not get anything, right? Or maybe like there is something like this, the last 2 guys does not get anything, right? So this is possible. But yeah, now all we have to do is to find the number of possible arrangements of the laddus and sticks. But this we already know, right? Because we already said that, right? If you have, so laddus are one type, right? So there is n objects of type laddu, and then k minus 1 objects of type stick, right? So we want to arrange the laddus and sticks in any possible way, right? So how many possible arrangements are there? By the multinomial theorem that we studied, right? If there is n1 objects of type 1 and n2 objects of type 2, the number of permutations of them is basically n factorial by n1 factorial into n2 factorial. So therefore we have n laddus and k minus 1 sticks. So n plus k minus 1 total objects are there, out of which n of them are of one type and k minus 1 of them are of different types. So therefore n plus k minus 1 factorial divided by n factorial into k minus 1 factorial, which is precisely n plus k minus 1 choose k minus 1 or n plus k minus 1 choose n, whichever you want, right? So therefore by the multinomial theorem, we immediately get that this count or the number of possible arrangements or the number of weak compositions is equal to n plus k minus 1 choose k minus 1. So that is it. So we have another proof. Okay. Now here are some homework questions for you. First is that you count the number of compositions of n if any number of parts are allowed. Okay. So what do I mean by that? So earlier we said that we have a fixed number of k parts are there, right? So we counted for precisely k. Now you want to find out for arbitrary number of, where k is arbitrary, right? It can be 1, it can be 2, it can be 3, etc., right? Now, can you find a closed formula for this, right? Now, closed formula is a formula without the summation sign. So I don't want, because you can always write, summation k is equal to 1 to blah, 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 n plus k minus 1 choose, what is that? N minus 1 choose k minus 1 or something like that, right? So this is very easy to write because we already know for any fixed k, you can always write a summation formula like this. But we don't want that summation form. We want the closed form where you find the formula without using the summation. Right? So you basically do the summation and give me the formula, or find another way to find it directly. So whichever way you want, you can do it. And the second part of the question is that what difference it makes if we allow the composition to be weak composition. Okay, so in the first part we are saying that count the number of compositions of n, you find the closed formula. Now the second question is that what difference makes to this closed formula if we allow the weak composition instead of the composition. Okay. So this is one question for you. Now, here is another interesting question that we want to look at. Suppose you have some kids maybe, right? A son and a daughter maybe, and then you invite their friends to come for a sleepover. Okay, so they come and stay for a night. So their friends arrive, and then there is total 10 kids, including their friends, right? The children and their friends together, there are 10 of them. Now, when there are 10 children, you cannot put them all into the same room because the rooms are generally easy to accommodate 10 people. So they will say that okay, we don't mind if you all want to put in one one room, but let us not do that. We will give you 3 rooms and you must use the 3 rooms to sleep, right? So, or let's say 4 rooms, right? In the question we are given 4 rooms. Okay, so we are given 4 rooms to the 10 children. Now say that okay, you go to the 4 rooms and then whichever groups you want, you can form, right? Who are want to sleep with others, decide and then go and find the corresponding rooms and then let us know and then go to the rooms, right? Now how many different ways this can happen, right? Because depending on the children's preference, right, whom to group with, there could be many possible ways to do this, right? So how many different possible ways this can happen. So how do you solve this, right? If you ask this, then there is something which is not very clear about this question, right? So what is not clear is that when we say how many different ways, what exactly do we mean? Because I can say that, okay, the children, let's say A, B, and C are going to the room number 1, because I gave 4 different rooms, right? So room number 1 is not the same as them going to room number 2, right? Because rooms are distinct, right? If I consider the rooms are distinct, then they are not the same. But maybe if you don't consider the rooms, I gave you 4 rooms, doesn't matter. What matters is the way the children are grouped together, right? I want to just see that who are all going together to sleep, right? But if I also want to know who are all going to which room, then that is a different question. So there are 2 different questions one can bring from this. Now, both of them can be interesting questions, right? So therefore, we want to look at both of them, right? So what happens if when the which group of students or children go to which room is important, and what happens if the rooms are not considered different? That is, which group goes to which room is not important, but what kind of groups are formed is only the interesting part. Now, if you think about it, you can see that these 2 questions, even though can be very different, in their values, they are very related as well. Okay. So can you think of some argument to say that solving one is, like solving the other also, in some sense. So this is an easy observation, but I want you to think about this. Okay. So think about it and tell me why solving one is as good as solving the other, right? Once you get an answer to the first one, you know how to solve the second one, or vice versa, right? So again, I don't want to give all these small whys, right, answers to all these small whys, because if you don't think about this, you are never going to learn things. So therefore, some of these questions, when I write just why and don't explain why, it should be something which, if you think about for some time, you should be able to come up with. It's not going to be a very difficult thing, but something interesting, and you should be able to come up with that argument. If you're not able to do that, then there is something that you have to work more. Okay. So hoping that you solve, let us continue. Now uh, let us look at more general statement of what we were looking at. So let k less than or equal to n be positive integer. Okay, so n is a natural number again, and k is also a natural number. Now a partition of this set, let's say set 1 to n, right, into k blocks is a set of k subsets of the set 1 to n. Let's say b is equal to set b1, b2, etc. bk, right, where bi's are blocks, such that bi intersection bj, where I not equal to j, is empty, that they are disjoint, right, pairwise disjoint, and their union bi is equal to the whole set, right, set 1 to n. So I think I already mentioned this notation that I will use, the notation that within the square bracket n is the set 1 to n. Okay, 1, 2, 3, etc. n. Now, so what we have defined here is a partition of a set. Okay, so a set with n elements I am partitioning into k blocks, such that they are pairwise disjoint and the union is the whole set. And now we want to find the number of possible such partitions. right? Number of partitions of the number of partitions of the set n or 1 to n to the k blocks with this property is called a partition. Yeah. So we want to find out such a number of such partitions. Okay? So we want to count them. And if you just look at this definition, it will be very clear that the earlier question that we were looking at regarding the children sleepover party was precisely the same, right? In some case. Now here is an example. So if you take the set 1, 2, 3, 4, then you can partition this set into 3 blocks, right? In 6 different ways. Okay? So I want to partition it into exactly 3 blocks. Now that can be done in 6 different ways. That is the claim. So let us look at the 6 sets that I am going to give and see whether they are the partitions first. So here is the set. Set 1, 2, set singleton 3 and singleton 4. That is the first partition. Then set 1, 3, singleton 2 and singleton 4, and etc. etc. Set 3, 4, singleton 1 and singleton 2. Right. So these 6 we can see that they are each blocks are disjoint in each of these partitions, right? So if you take any of these, the elements does not repeat, and they form the all elements appear there, so therefore the union is the whole set. So these are all partitions, and we have exactly 3 blocks, right? A 2 element set and 2 singletons. And since we want 3 blocks and we have only 4 elements, the only way to partition is to have like 2 in one set and 1 and 1 in other sets. And this will tell you why we can only have 6 possibilities, right? So maybe you argue it slightly more formally, right? Why only 6 are there? So 6 are already there, but why there are no more, right? So give me an argument for that. Now, another example, but I want to do this as a kind of homework example, or maybe not. Maybe why don't we do it here? So there are 25 partitions of the set 1, 2, 3, 4, 5 into 3 blocks. So we said that when there are only 4, right? 1, 2, 3, 4, number of partitions into 3 blocks is only 6. Now when you add one more, we have 25 of them. Now how is this exactly 25? Can you give an argument why this is 25? Okay. So maybe you should stop and think about this for some time before going further, because if you can do it on your own, that is the best. Okay. Now let me give an argument. If you have thought about it for some time, please continue. So we are looking at the partition of set 1, 2, 3, 4, 5, right? So there's exactly 5 elements. 1, 2, 3, 4, 5, right? Into 3 blocks. 3 blocks. Since we are looking at exactly 3 blocks, what we can observe is that the only possibilities are you can have elements, the sets, in the partition be of cardinality either 3, if there is 3, and since we need exactly 3 blocks, if you take 3 elements into one set, the other 2 must be 1, 1, because there is only 5 of them, right? So it should be like something like cardinality 3, 1, 1. This is not the set 3, 1, 1. This is not set 3, 1, 1. So we should have the blocks of cardinality 3, 1, 1. This is one possibility. Other possibility is that you have 2 one subset has 2 elements, then since there are only 2 more and we have 3 elements, so we need to have another 2 and then 1. And you cannot put 4 into 1. You cannot put 1, 1, 1, 1, 1, etc. because you are only allowed 3 blocks. So one can verify that the only 2 possibilities are blocks of size 3, 1, 1 or 2, 2, 1. Now, once you observe this, well, we know that since we have exactly 3 blocks and you select the first, let's just concentrate on this part, right? 3, 1, 1, right? Suppose you select a 3 element subset from the 5 elements. So which means that how many ways you can do this? You can do it in 5 choose 3 possible ways, right? Once you choose the 5 choose 3 possible ways, so what is 5 choose 3? 5 into 4 into 3 by 1 into 2 into 3, which is 10. Right? So in 10 possible ways, I select this. Then we have only choice is to take the remaining 2 elements as singletons, right? So there is 3 elements are already gone. The remaining 2 must be singletons and there is no choice there. So we have exactly 10 possible ways to do this. Now on the other hand, if you look at the 2-2-1 configuration, then you can see that if you choose, let us say, 2 of the elements, right? In the first, how many possible ways? 5 choose 2 possible ways, right? 5 choose 2 possible ways, you select the 2 elements, right? First 2 elements. Then to select the remaining 2 elements or 1 element, right? Once you choose 1 element, it is very clear what are the other 2 elements going to be. Or if you select the 2 elements again, it will be clear what is the remaining 1 element, right? So the remaining 2 elements can be chosen in how many ways? Another 5 choose 2 possible ways, right? I mean, not 5 choose 2. The remaining is 3 choose 2 possible ways, right? Then the last one, there is no choice. But there is a problem. If you use the product rule here, like 5 choose 2 and 3 choose 2, then what you will get is that 5 choose 2 is 10 and 3 choose 2 is 2 is equal to 30. But I claim that this is wrong. Why is this wrong? This is wrong because when we were doing the counting, we did some over counting. Can you think of why there is some over counting? Okay. So the reason there is an over counting is that when you selected the first 2 element subset in 5 choose 2 or 10 possible ways, and then you selected a 2 element subset from the remaining 3 elements, the 2 element subset that you selected in the first and the remaining 2 element subset you selected in the second could also appear as those 2 elements were selected in the first choice and the other 2 elements were selected in the second choice. So in these 2 possible ways it can come, and we are counting both of them when you take the multiplication. So therefore, since we are counting each of these exactly twice, we can divide by 2. So we will get 10 into 3 divided by 2, which is equal to 15. So I have 15 possible ways only, not 30 possible ways. And therefore, the total number of such partitions into blocks is 15 plus 10. 15 plus 10 is equal to 25. Okay. So we need to be very careful when we do this kind of counting, because over counting must be avoided, right? Or if you do overcount, You have to find a suitable way to deal with that. Okay. Now, the number of partitions of an n element set into k blocks is denoted by S of n comma k. Okay. So these numbers that we are looking at, they have a specific notation. So if you are looking at n element set and you are looking at k blocks, then S of n comma k denotes the number of partitions of an n element set into k blocks. And this is called the Stirling number of second kind. Okay. So the number of partitions of a set into k blocks is denoted by Snk, and it's called the Stirling number of second kind. So one can ask, like, what happened to the first kind, right? Why we are not looking at the first kind before we look at the second kind? We will look at the first kind sometime in the future, but that is much more difficult to deal with. It's a much more involved computation, and we will look at those things in the later part of the course. So for the time being, we will stick with the Stirling number of the second kind. Now, how do you find SNK? Can you find a formula for SNK, or can you find a way to compute SNK? Right? These are some interesting questions one can ask. So I want you to think about these questions. And here are some observations. So SNK is 0 if k is greater than n, right? That is very clear. And Sn0 is 0 if n is greater than 0. That is also kind of clear why. And S of 0, 0 on the other hand is equal to 1, right? That is precisely one way to do this. Basically, there is nothing to do, right? So that is precisely the one way. Now, S of n comma 1 and S of n comma n are always going to be equal to 1. This is also another observation. You should verify that, whatever I claim, don't take it for granted, right? When I say something and you think that why it is that case, it means that you are supposed to figure it out yourself. Okay, think about this and find out why. And they are kind of easy questions. That's why I'm giving you it as an open, just a statement without any argument. Okay, so if I figure out why these things are the way I have defined it here. Now, to come up with solutions to this, we might need to use some new ideas. So one of the ideas that of called recursion. Okay. Now, suppose you are given a sequence of, let's say, unknown values, right? So let's say A1, A2, A3, etc. Right? Is given sequence of unknown values. Now, what we want to know is that we want to find out a way to find, or describe, let's say, an. Okay. So suppose I write an is equal to f of n, where the right hand side expression, okay, the right hand side expression does not, the right hand side expression does not depend on any of the AIs, but it depends on n, right? It can depend on n. Okay, so if n is equal to f of n, where the right hand side is an explicit formula without depending on any of the AIs, any of the unknowns, but it can depend on n, is called a closed formula for n. Okay, so it's a closed formula for n. Now, on the other hand, a formula of the form an is equal to f of, let's say, n comma a0, a1, a2, etc., an minus 1. I mean, this can be something, other than an minus 1, but something less than n, of course. The index should be less than n. Together with some initial conditions like, a0 is something, a1 is something, etc. Some of the things can be already given, which are not defined recursively. They are given explicitly. then such a statement is called a recursive formula for an. Okay, so an depends on some previously determined unknowns and n also, but it does not depend on anything that we have not come across so far, right? So such a description is called a recursive formula. Okay. So basically, if you know, right, the some of the initial values, you should be able to find the next one, right, which is not known. Then using that, you can find the next one, right, in a recursive manner. That's why it's called a recursive formula. So let us look at an example, right? So for let's say n greater than or equal to 0, let's define p subscript n, be the set of all subsets of the set 1 to n. And let us define an to be the cardinality of pn. Okay. So this is something most familiar to you, right? So basically, you are looking at the power sets of the sets that we are talking about, right? Set of all subsets of 1 to n. So power sets of the set 1 to n. And we want to find out what are the cardinalities, right? We already know how to do it using the product rule we did long time back. But now we want to use and try to solve it using a recursive formula. So we come up with a recursive formula and try to prove it, to solve it and get an answer. So for let us say solving something like this, what we can do? Well, what we can do is that we can do some observations, right? So we observe that a0 is equal to 1, right? Because a0 is the cardinality of p0, right? And p0 is the set of all subsets of the empty set, which is the set containing empty set. And its cardinality, because it is singleton, the cardinality is exactly 1. So a0 is 1. So we get an initial condition. Now we need to find the recursive relation. Okay. So to find the recursive relation, what we do is the following. Let me just erase this. So we do the following to find a recursive relation. So what is that? So given, let us say, given, let us say, n is greater than or equal to 1, to construct or to build any subset, let's say S in Pn, what we can do is the following. Okay. So to select such a subset, we will select the any subset, let's say S dash of the subset 1 to n minus 1, right? So we remove the element n and look at the set 1 to n minus 1. So look at the subsets in P n minus 1, right? So this means that S dash belongs to, S dash not belongs to, S dash is a subset of the set 1 to etc. n minus 1, right? So S is some subset of 1 to n minus 1, and then we will select the element n and say that, okay, now I have two choices. One is either to add n to this set S dash to construct a subset of Pn, or I don't add it, I just keep it as it is, right? So there are these two choices. Either I add this element to that set or I keep the subset as it is. Now this way I can create all possible subsets of Pn, because I take all the subsets of 1 to n minus 1 and then I add n or I don't add n, right? So I will get all possible subsets this way. So there are two choices. Either add n to s dash or not add n to s dash. Okay. So now, once you know this, using the product rule, we can we can figure out that an is equal to 2 into an minus 1, because whatever is the number of elements in in Pn minus 1, we are doubling it, right? Because I take this guys, any element here, I add n or I don't add n, both way I get a subset of Pn, and therefore I get 2 times of this many, which is 2 times an minus 1. So for any n greater than or equal to 1, we have an is equal to 2 times an minus 1. Now with the initial condition that we figured out, that is a0 is equal to 1, we can now try to find out the values of an, right, as follows, right? A0 is equal to 1, therefore a1 is equal to 1 into 2, which is 2, then a2 is equal to 2 into 2, which is 4, then you get 8, 16, etc. for a3, a4, etc. So we find out what are these numbers. So now from this we can guess, right? We can guess the value of an, right? We see that an is something like 2 raised to n, right? N is 2 raised to n. And then once we find the guess, we verify this and we can use induction to prove it actually. So how do we do that? So we do the following, right? We guess that n is equal to 2 raised to n, and to prove we use induction. So the base case is n is equal to 0. A0 is, we already know that it is 1, which is 2 raised to 0 also. So therefore that is okay. Base case is fine. Now we take the case n is equal to 2 into an minus 1. And by induction hypothesis, for an minus 1, it is 2 raised to n minus 1. And therefore this is equal to 2 into 2 raised to n minus 1. But that is equal to 2 raised to n, right? So therefore n is equal to 2 raised to n, which proves our hypothesis. Therefore we have the proof, right? So therefore by induction we get that n is equal to 2 raised to n. So if we can guess what is the close formula for an, most often we can use induction easily, because we know, like a1, even though it may depend on, like a1, a2, etc., n minus 1, since we know that each of them has the same formula, we substitute that and then try to figure out why the recursive relation must satisfy this, and if it satisfies, then we get that it is indeed the case. So this way we have proved it. Now homework. This is a question that I want you to think very thoroughly about. It's a very interesting question. Okay, and this question has been solved in by the Indian mathematicians many years before, and so you should be able to, thousands of years before, in fact. So I want you to think about this and try to see how you will solve this, and how you form a recurrence relation for this, for example, right? So here is the question. So in a certain type of poetry in Indian languages, like Malayalam, Sanskrit poetry, the syllables of length 1 and length 2 are allowed, right? So each letter can be either short or long, right? A, right? Ka, etc., right? So we have this long and short syllables. We will say that Lagu, the short one, and Guru, the long one. The long one has exactly twice the length of the short one, and that is a long accepted convention, right? The long one is A, and A are exactly the second one is twice the length of the first one. It's supposed to be like that. Even though we don't do it precisely when we talk, it should be exactly like that. So the syllables of length 1 and 2 are allowed. Now, the total length, you know, of each line in the poem is fixed to be a positive integer. In terms of the syllable length, right? It should be exactly the same, right? From certain kind of poetry. So we'll say that, okay, we will allow exactly, let's say, length 5, right? Syllable, whatever you use, it should be of length 5. So you can have maybe 5 lagus, right? 5, lagu, right? Right? So there are 5 of them. Or you can have maybe 2 and 1, 1, 1, or 1, 2, 1, 1, right? Or 2, 2, 1, etc. All these possible lengths are allowed, right? So, once the length of each line is predefined, something like this, this kind of a pattern we can decide. So once you decide a pattern, that such a pattern is called a meter, right? For example, LLG is a meter with length 4 because LL 1 1 and G has 2, right? Guru has 2, Lagu has 1. So 1 1 2, it has length 4. And GLG has length 5 because it is 2 1 2, right? Length 2, Guru has length 2, then Lagu has 1 and again 2. So formulate a recursive formula to count Fn, where Fn is the number of different meters of length n. Okay, so some formula, define F0, F1, etc. You find some initial conditions and write a recursive formula to define Fn. And then if you can solve the recursive formula, well, even better. But at the moment, I want you to come up with a recursive formula for this. So this is what I want you to do. Now, before we finish today, let me state a theorem and you think about the proof. So the theorem is the following: for all positive integers k greater than or equal to n, the Stirling number of second kind S of nk is equal to S of n minus 1 k minus 1 plus k into S of n minus 1 comma k. So it satisfies this identity. Right? For every n comma k where k is greater than or equal to n, S of n comma k is equal to S of n minus 1 comma k minus 1 plus k into S of n minus 1 comma k. So can you find an argument why this is the recursive formula for Snk? So this is the recursive formula definition for Snk. Right? It depends on S of n minus 1 k minus 1 and S of n minus 1 k, and recursively it can depend on the previous ones, right? Basically. So this is what I want you to do. Okay, so think about how to do this, and we stop for today. We will continue with the proof of this and other results in the next lectures.